Okay, let's get started, please. So today we're going to talk about instantaneous rate of change. The idea is like this. You have a car, so have a car. Right, so the car is traveling along a linear track. So here's your car. It's going along this track. And you are talking about how fast the car is moving. Okay, so how fast is the car moving? Right, you want to know like how fast the car is moving. Okay. Or if you don't like cars, you could think about maybe you have a kid, right? And every day or so, or every minute, or every second, or every year, you measure like how tall the kid is. Right, and you're wondering like how fast the kid is growing. Okay, whatever you like, either way. Okay, and so you're interested in this case, say the velocity, right? So that would be well, you'd say like how far has it moved? So the distance traveled. Traveled over the length. In what length of time? Right? That's going to be the rate of change of position, right? With respect to time, right? With this WRT is with respect to time, right? And similarly here, it'd be rate of change of height, rate of change height with respect to time. Okay. So how do you figure out how fast the car is moving? Right, you measure where the car is at some point in time, and then you wait a certain period of time, and then you measure where the car is. And you say, okay, how far did the car move, and how long was the time, right? And you divide the distance traveled over the length and time, and that's the the average rate of change over that period, right? So so you could say like how fast the car was over a 1 minute period, right? Or how fast the car was over an hour period, or this sort of thing, right? There's the old joke about somebody who gets stopped for driving 60 miles an hour in a 30 mile per hour zone, right? And the policeman says, did you know you were driving 60 miles an hour in a 30 mile per hour zone? And the person says, well, I was only going to drive for half an hour, right? Right? I was only going to drive for half an hour, so in that 1 hour I would have driven 30 miles, right? So of course that's not what the speed limit refers to, right? The speed limit refers to how fast you're moving at just that moment, right? It refers to some sort of instantaneous velocity, not the average velocity over the hour, right? But that's a reasonable thing to say, right? My average velocity over this hour was only 30 miles per hour, right? That's what it says on the sign, right? 30 miles per hour, right? Okay, so how do you? But then how do you talk about instantaneous velocity? Well, does it make sense to talk about instantaneous velocity? Right? If I take a picture of you, if I took a picture of the car at one instant in time, then how fast is it moving? Right? If I show you a picture of a car, okay, here's the picture of my car. How fast is it moving? Right? You don't know, right? Because it doesn't make sense to take instantaneous velocity, right? You need to have some distance traveled. If it's just an instant, right? If it's just an instant, then there's no distance traveled, right? There's no distance traveled, right? So it doesn't make sense to talk about. Right, so it makes no sense to talk about instantaneous velocity. Instantaneous velocity, right? That's basically an oxymoron, right? A contradiction in terms, right? And instantaneous makes no sense to talk about instantaneous velocity, but we do anyway. Right? Instead, so what we do is we talk about the limit. We talk about the limit. Okay. So if we wanted to know, let's say that so let p of t be the position of the car at time t, right? Or if you like height, right, the height of the child, at time t, right? And right, if we want to know, say we want to know the instantaneous velocity at time t naught. At time t naught. So at 12 o'clock noon, how fast was this car moving? Okay. What we do is consider this. We what if we want to consider the instantaneous velocity, right? Really, there is no instantaneous velocity. So what we do is we look at this. We say, well, let's look at p, the position. Let's look at this difference, right? The change in position. You take some small time interval h, right? Your time interval is like 1 minute. Say it's 1 minute. Say I'm going to take my time t naught and add on 1 minute. So noon, 12:01, position at 12:01 minus position at 12, right? So over that 1 minute, and then I'm going to divide by the length of the time period, right? And that would give me the average velocity over that 1 minute, right? That will give me the average velocity over that 1 minute, right? And then what are we going to do with this? Does we know? We're going to let h become arbitrarily small, right? We're going to let h tends to take the limit as h tends to 0. That is, we'll consider, for example, the time that the change in position over 1 second, noon plus 1 second. What's the position at noon plus 1 second minus the position at noon divided by 1 second? 1/10 of a second, 1/millionth of a second, et cetera, et cetera. And although we can't talk about the instantaneous velocity, we can talk about this limit, right? We can talk about this limit. This is something we know how to do, right? And we define this thing to be the instantaneous velocity. So we call this limit, if it exists, the instantaneous velocity. Okay. Sometimes people write it like this. Sometimes you write it like this. The limit of p of t minus p of t naught over t minus t naught as t goes to t naught. That's the same thing, because you're taking t at some time close to t naught. You're taking t at some time close to t naught. You say, okay, I'd like the change in position between that close time and the actual time, and then the time interval over what time interval. Okay, so these two things are exactly the same. Yeah, Rachel.
So you keep saying the instantaneous velocity doesn't really exist,
Yeah.
and then we're trying to find it.
Yeah. Okay. I mean, instantaneous velocity really is not something you can talk about, right? There is no instantaneous velocity, but we call this thing the instantaneous velocity. Okay. We call this thing the instantaneous velocity. Here it is. Right? We don't. You can't. We're gonna consider this thing to be the instantaneous velocity, right? Are there other questions? Yeah. Even if it doesn't exist, we're going to make up something and call it that. It'll be the limit of the change in positions over the change in time as the time interval becomes arbitrarily small, right? So that's as good as one can get. That's as good as one can get to something which doesn't exist. Okay. Any questions? Any questions on the idea? Any questions on the idea? Right. So we have this thing. The velocity is easy, right? You just take the change in position over the change in time, right? We'd like to know the instantaneous change in position over the change in time. There's no such thing, but we take the limit, and that's something pretty close to it. Something that we'll use for it. Yeah. And it turns out to be a very, very useful notion.
So
Yeah.
that may be really off, but is this like when you said we were doing fractals and it gets smaller and smaller and smaller and smaller and it just gets more complicated? Is it at all related to this? Like as you zoom in, it just the like equation you know is just crazy.
It's related in the sense that you're letting things become arbitrarily small. Let me try to tie it in a little bit later. Yeah, let me try to tie it in a little bit later. Okay. Okay, so that's maybe like a physical or biological introduction to instantaneous rate of change. If we want to look at it graphically, say with functions, right? The graph of a function. Suppose you have some function. Here it is. Pi of x, right? So here is x. This height, of course, is pi of x. Okay. And we have x plus h here, and this height is pi of x plus h, of course. Right? That's the graph. This thing is the graph. Of this function. Graph of this function, right? So we can consider the slope of the secant line. So we can consider the slope of the secant line through these 2 points. We can consider the slope of the line through these 2 points. Well, what's the slope?
Change in y over change in x.
Change in y over change in x, right? So pi of x plus h minus pi of x over x plus h minus x, right? The change in y over the change in x. Right? That's pi of x plus h. Right? So that's the slope of this line here. Right, this line is called the secant line. This line is called the secant line, and the slope is this. Okay, and just as before, maybe we would like to know the slope of a line that just touches the graph here. Right, we'd like to know the so-called slope of the tangent line. Right. Or if you want, you can say you'd like to know the slope of the instantaneous secant line. Right? You'd like to know the slope of the instantaneous secant line where h is 0. Okay. Okay. Again, of course, there is no instantaneous secant line where h is 0 because then you've got only 1 point. Right? How do you determine your line with only 1 point? With two points, you can determine a line. 1 point, you don't determine a line. Right. So you'd like to be able to talk about the slope of the instantaneous secant line, aka the tangent line. Okay. But it's impossible, and so instead, what you do is, right. So we'd like to ask, what's the slope of the secant line where the second point is also at x. Okay. That's what we'd like to do, but it's not possible. So just as before, right? we call, as before, we call the limit as h goes to 0 of this thing, the instantaneous slope. The instantaneous slope, or more properly, the slope of the tangent line. Okay. So this thing is called the slope. You have some curve, right? And you'd like to be able to draw the line that just passes through, right? Suppose you have something like this, circular arc, and you'd like to have a line that just passes exactly through that point and hits nothing else on this circle. Okay, right? Can you do it? It's not so easy, right? If you are, right, suppose you have this circle here, right? If you are off by even the slightest, well, you're going to hit it in two places, right? Right? If you're off, if you don't get exactly the right number, and that's down to an infinitely many decimals, right? Right? Then you're going to hit in two places, right? Can you find the slope of the line through slope of the tangent line through a circle? At some point that I give you, it's not so easy. It's not so easy. If you look in your text, you'll see that that this method was basically pioneered by Fairmont. Fairmont, the lawyer Pierre de Fairmont, who's famous for Fairmont's last theorem. Do you know this? Fairmont's last theorem? Oh, okay. So in any case, in your book, they talk about how Fairmont and Descartes had this sort of violent, like hate relationship of hate, where they wrote angry letters to each other, and Descartes. Well, as usual, my history. You don't believe what I'm telling you. This is not really history. In any case, go read your textbook. Descartes and Fairmont did not like each other. Fairmont showed this method. Descartes disparaged it. Ultimately, he sort of grudgingly said, "Okay, I guess you are right." Maybe a better story is the story of Fairmont's last theorem. If I can do it in 2 minutes, maybe it's certainly worth talking about for more than 2 minutes. But let me try to give you a quick story. So there's this Fairmont was a lawyer, and he in his spare time he liked to do mathematics. In fact, he was a great mathematician, and so he would come up with things that other people had not. He'd try to figure out things that other people had not figured out, and then he'd send out a note saying, "I have figured out how to show this amazing fact, and I challenge you guys to do it." And so the mathematical community would always receive these notices from Fairmont, saying what he had done, and then they'd have to see if they could do what he had done in his spare time. When he died, there was this book that he left, and he had left a long list of things that he said, "I've proven this, I've proven this." All these things were things that he had done and which nobody knew how to do. There was one statement. So over time, the mathematicians in the world, got one after the other, and finally there's only one left. Okay? And that's what they call Fairmont's last theorem. Even more irritatingly, he left a note saying, "I have discovered a truly marvelous proof of this fact, but I cannot fit it in the margin here." And then, he's dead. Okay. So, the theorem has to do with the Pythagorean theorem. The question whether or not you can find, so in the case of the Pythagorean theorem, you can find whole number solutions. right? 3 squared plus 4 squared is 5 squared. 12 squared plus 5 squared is 13 squared. 5 squared plus 12 squared is 15 squared, etc., etc., right? The question for the Fairmonts' theorem says this. If you change this to any number bigger than 2, then there's no solutions. There's no whole number solutions. If you change this to any number, so for 3, there's no solutions. For 4, there's no solutions. For 5, there's no solutions. For 6, for any number you choose, there's no solution. Okay, and this theorem nobody could prove for 350 years. So it took 350 years. Finally, in 1993, Andrew Wiles of Princeton University, who I had the honor of taking my first math class with. I wasn't there at the time, but so after I graduated, Wiles announced to the world that he proved Fermat's last theorem. And so there's more of a story than this, but maybe I'll let you guys watch the movie at some point. There's a movie about it. Yeah. So ultimately, it's ultimately he was the one who did it. He was the one who did it. So he got it. Yeah.
But it took 300 pages or a book or something like that.
Yeah. It's a gigantic proof. It's a using all the machinery of 20th century number theory. So things that did not exist at the time of Fermat. It took a lot.
So we don't know how Fermat actually proved it.
It's likely that he didn't. It's likely that he didn't have proof of it. Because you see that in order for Wiles to get it, he had to use basically 20th century technology to do it. Yeah. People suspect that he had a proof. So in I think there are a couple of people who proved some of the lower cases, like n equals 3 or n equals 4. And they used it by using some method that I don't remember the name of. And people suspect that he probably had that method and thought that it would extend to all cases. There was a funny article in the newspaper at the time about how graduate students at the University of Chicago rioted to celebrate Wiles' proof of Fermat's last theorem. That they stopped laymen on the street and asked them mathematical puzzles and overturned cars and set fires and things like this. Actually, we didn't do anything like that. I was actually there. We didn't. Okay. Enough entertainment. Okay. So instantaneous slope. So let's do an example. So the slope of the tangent line. So for example, if somebody gives you this, here's a parabola, right? And they say, here's some parabola, and they'd like to know the slope at some point. The slope of the tangent line at some point. So let's say we want to know the slope at some point x naught. Okay, so there's some x naught somewhere, and you want to know the slope of the tangent. Okay, so let's see how you do it. Take a minute and see if you can just set up the limit that you need to use to figure out the slope of the tangent. Take 1 minute. Okay, turn to somebody next to you and say, here's what I wrote down. Okay, so what limit do we need to consider? Right, the slope of the tangent line at x naught is going to be eliminated as say h goes to 0 of what? Yeah, how?
So just start f of x plus h minus f of x over h. And then you plug in the value of f of x. So you plug in x naught plus h into the f of x.
Okay, so we get x naught plus h, and we plug that into our thing here. We get x naught plus h squared plus x naught plus h plus 5, right? And then we subtract off, that's our first term, we subtract off x naught squared plus x naught plus 5, everything over h, right? Take the limit as h goes to 0. Right, and we work it out, right? This is going to be x naught squared plus 2 x naught h plus h squared plus x naught plus h plus 5 minus x naught squared minus x naught minus 5 of h. Right, the x naught squareds cancel out, the x naughts cancel out, the 5s cancel out. Right, you get the limit as h goes to 0 of 2 x naught h plus h squared plus h over h. Okay. Let me write that up here. 2 x naught h plus h squared over h as h goes to 0. Okay, right? And what's that?
Can you factor out the h?
Mm-hmm. You factor out the h, right? Limit as h goes to 0 of 2 x naught plus 1 plus h as h goes to 0. So what's that? Thank you. 2 x naught plus 1. 2 x naught plus 1. Okay. So that tells you, for example, that if you're looking for the slope of the tangent line at 0, right, the slope of the tangent line is 1 at 0, right? The slope of the tangent line is 1 at 0, right? At 10, the slope of the tangent line is going to be 21, right? It tells you the slopes of the tangent lines, right? And it tells you how the slopes of the tangent lines change, right? The slopes of the tangent lines change in this linear manner, right? At 0, it's 1. At 1, it's 3. At 2, it's 5, right? At 3, it's 7, etc., right? They change. The slopes of the tangent lines change in this linearly increasing manner, or decreasing if you're going backwards. Okay. Right? At -1, it's -1. Right? At -2, it's -3. Etc. Okay. Okay. So that's pretty cool, right? You get to see not only what it is, but how exactly it changes. Okay. Any questions on how we did this? Any questions? Okay. Okay. Another example. Suppose your I of x is, say, x to the 6, right? And somebody wants the slope of the tangent line at at some point x naught. let's do this. Let's do this one together. What will we need to do? What limit do we need to consider? The limit as h goes to 0 of what? Shrug. I mean shrug. Shrug. Sorry. Shrug. What do we need to do? Right, slope of the tangent line at some point. So we take the limit of, you don't know. That's okay. I'll go.
Did you just plug x to the 6 into the equation where we used x sub 0?
Say it again. Plug, what do you mean plug x to the 6 into the equation? It's sort of, in some sense.
Oh, right.
So tell me what I wrote here.
Did you write f of...
I'll use pi. I'm using pi, so it's like pi of
x sub 0?
Mm-hmm. People usually call this x naught or not. X naught. Like nothing.
X naught, okay.
Yeah.
Plus 8
Mm-hmm.
minus pi of x
Pi of x naught. Mm-hmm.
over h.
It was all for naught. My teaching was all for naught. No. that not the knot that I'm using right now. Okay. Right. So what's this? Right, this is kind of the limit as h goes to 0 of x naught plus h to the 6th minus x naught to the 6th over h. Right. Okay. Take half a minute and see what this is. Or think about it. Okay. You don't have to try. You don't try to multiply it out, but think about what happens. Okay. Try it. Okay. What's the answer? Right. You get x naught plus h to the 6th. Right. Those of you who are familiar with Pascal's so-called Pascal's Triangle, right? Know that it gives you the coefficients to a product to some power. Right. If you're looking at, say, if you're looking at a plus b squared, right, you get a squared plus 2ab plus b squared, right? If you're looking at a plus b cubed, it's a cubed plus a squared b plus ab squared plus b squared, b cubed, right? right, et cetera, et cetera. So if you don't want to think about it, you could just say, I remember Pascal's triangle, right? It's going to tell me that this is going to be x naught to the sixth plus 6 x naught to the fifth h plus 15 x naught to the fourth h squared plus 20 x naught cubed h cubed, et cetera, down to h to the sixth, right? Everything over h. Right, up, we got to subtract. Right, we got this guy. Okay. Joey, what's wrong?
I'm just looking at it.
Okay. Should I write everything up? Yeah, we should write everything. That's 15 x naught squared h to the fourth plus 6 x naught h to the fifth plus h to the sixth minus x naught to the sixth. Okay. 1, 6, 15, 20, 15, 6, 1. Just like in the triangle. Okay. And then you just do the same thing as before, right? The x naught to the 6 and the x naught to the 6 cancel, right? And you see that, does anyone see what happens here? Here we get this 6x naught to the fifth h over h, so those h's cancel, right? And then everything else, what happens to everything else? Joey, come on.
H remains.
The h remains, right? We get some power of h, right? Here we get h, here we get h squared, h cubed, h fourth, h fifth, right? So you get everything that remains has some power of h in it, right? It's h times something, okay? And we take the limit as h goes to 0, right? So everything, the other guys are just going to vanish, right? And so you end up with 6 x naught to the fifth. Any questions about that? This is basically the same thing that we did over there with the quadratic, except now we've got something to the 6th power. That's the only difference. But you see that this exactly the same sort of thing happens, right? This is no more difficult. It's just longer. Right? Just for your amusement, if you tried to multiply this thing out, the six of them, right? You could say like this. You'd say, well, look. I can take x naught, x naught, x naught, x naught, x naught, x naught, right? That's the only way I can get x naught to the 6th, right? How many ways can I get x naught to the 6th? Only by taking this. Only by taking choosing the first guy each time, right? So I know that there's only one x naught to the 6th, right? How about x naughts to the 5th, right? How many x naughts to the 5th do I have? Well, if I choose h here, and x naught everywhere else, that's 1, right? So I have 1. Or if I choose h here and x naught everywhere else, that gives me another, right? And if I choose x naught here and h here and x naught everywhere else, then I get another, right? And you see that I can get a total of 6 of these guys, right? There's 6 ways to get x naught to the 5th, right? Right, 6 h ways to get 6 times h ways to get x naught to the 5th. Okay, right, and then you could go on from there. But if you know what's going to happen, you see that the other guys are going to vanish anyway, and so you can sort of stop there if you want. Anyway, don't worry about it if it doesn't make any sense. Yeah, Alfred.
I have a question
Yeah.
on I guess this isn't related to what we did, but it's to the function, like pi of x.
Mm-hmm. Pi is just a name, like f.
Oh, okay. So You don't multiply pi or anything?
No. This is just a letter, like p. Should I call it p?
Oh, okay.
P of x, p of x, p of x. Pi is just a letter. And if you look in a Chinese mathematical journal, they'll sometimes use Chinese characters as symbols, right? Instead of like f of x, they'll say like f of some character or something. Yeah, or they'll use characters for the names of functions instead of alphabetical letters. Okay. Okay. So for example, so let's go to let's use this for something. Okay, so here we know that the slope of the tangent line to x to the 6th power is 6 at x naught is 6 x naught to the 5th. So for example, at the point 2 to the 6th, right? This is a point on the graph, right? Here's 2 and then 2 to the 6th. Right? You have this thing. This is your x to the 6th function, right? And you want to know the slope here, right? Well, the slope is just going to be, the slope is 6 times 2 to the 5th. Right? 6 times 32, that's to say 192. Right? So you know that the slope is 192 at that point. And if somebody asks you for the equation of the tangent line, you could tell them, right? What's the equation of the tangent line? Cynthia, go ahead.
6x naught. Wait.
So here's the point 2 to the 6th, and I have the slope of a line that passes through this point. Right? I have the slope of the line that passes through this point. I have a point, I have a slope. So what's the equation of the line? What's the equation of the line? Those of you who have been in this class? Sharon. Oh God.
Equation of a line.
Yeah, equation of a line, right? You know the slope, you know the point. Use the point. What? Here's the point, right? This is not an intercept, right? Use the point slope formula. You have a point and a slope. Why use the slope intercept?
Y2 minus y1. Right? Or something like that.
Something like that.
Is that the one?
Y minus the y value equals. Very good. Very good. And I shouldn't say that. Okay. At least this is it. Okay. Slope of the line. Slope of the tangent line. Right? Easy. Easy. Should be easy. Okay. Okay. One thing. Note that the limit may not exist. The limit might not exist, right? You're looking for, right, if you have some function that goes crazy, say, right? If you have this crazy function that we looked at earlier, say, like f of x is sine 1 over x, where x not equals 0, and it's say 0 for x equals 0, then that you're not going to get a slope of a tangent line out of that. Yeah, Taylor.
Okay, just to clarify.
Yeah.
The 6x naught to the 5th is the slope of the tangent line.
At x naught, yeah.
At x naught.
Yeah, slope of the tangent line to this guy at x naught.
And the equation that we just found
Gives us a specific one. So we're saying take x naught to be 2. Take x naught to be 2.
Okay.
Right? At time 2, if you take x naught to be 2, the slope of the tangent line there is 6 times 2 to the 5th.
Okay. So if the equation or the line changes depending on.
Oh, yeah.
Yeah. Okay.
Right? I mean, just look at it. Right?
Yeah.
The line changes, the slope changes. Right? The slope changes. It's negative, it's positive. Right? It changes. It changes exactly.
But you would just find it the same way, just using a different form.
Yeah, yeah. So at -1, say, the slope would be -6.
Okay.
Right? If I'm looking here, -1, the slope here is -6.
Okay.
And you know, figure out the tangent line there. Okay, so let me say a couple things before we finish up. Note that the slope the slope may not exist, right? You can have some function, the limit just doesn't exist, right? Or you could have something like this. You know, what's the slope of the secant line at this point? Well, on one side it looks like it's 1, on the other side it looks like it's -1. The limit doesn't exist because the limit doesn't agree from left and right sides. Right? So if f of x is at the value of x, then the limit, that limit doesn't exist. Okay. If the limit does exist, if the limit of f of x naught plus h minus f of x naught over h as h goes to 0 exists, we call it, let's say, it's finite, and it's finite. So I don't want to talk about an infinite one. We call this the instantaneous rate of change of f of x. Instantaneous rate of change of f at x. And more properly, it's called, actually, it's the derivative of f at x naught. Sorry, x naught. The derivative of f at x naught. And you denote it by this, f prime x naught. Okay. F prime x naught. If it's finite and exists. Okay. Just one thing. So just one more thing. I was hoping to get to it, but I don't think we will. So I was going to do one more example. If f of x is sine x, then it turns out that the limit of sine x plus h times sine of x over h turns out to be cosine of x. Using some trig formulas and using some identities that we've seen before. Please take a look at the last note in the notes. Okay. So this will probably turn up in your homework somewhere. So. Yeah, Ellie.
Oh, back to the absolute value one.
Yeah.
So can you have a period at every point except for the 21 matrix?
Actually, everybody, you can feel free to go. Maybe I'll just talk to you.
So can you have a period at all the other points?
Yeah.
Okay.
Yeah. So the derivative didn't exist at 0,
Okay.
but everywhere else it was. Thank you.
I wasn't feeling well this morning, but can we be at on time?
Yeah, I will be there.
Okay. What time would I get again?
I'm there from 1:30 to 2:30. So office hours, if it says office hours, it means I'm there.
Okay, thank you.
So I want to come to office hours today, but I have the Spanish conversation group technically from 1:30 to 2:30. But
Okay.
I'm going to ask if I can leave a little early.
Okay,
So
okay.
will you still be there if I come at like 2:30?
Yeah, I'm quite likely.
Okay.
Yeah.
Thank you.
Hi, Professor. I was wondering, can I schedule an appointment on a weekday other than Monday or Friday? this
Yeah,
week,
yeah.
Or
Sure. When?
can I just email it to you? Maybe
Yes,
like
yes.
Wednesday or something.
Yes.
Yes.
Wednesday might not be such a good day. I have to get my car fixed.
Okay. What day?
Tuesday is better. Tuesday or Thursday is
Tuesday.
better.
Meeting right after. Okay. And also, will we be testing on derivatives for this?
Everything up to today. Everything up to today.
So this isn't a.
So yes. What's that?
escalate, but that's not always like for other
Do you want it now though?
yeah.
Okay. Cool, we'll go here.
Oh, wait. I see. There were extra ones.
I haven't done like a final post for them, like for weird things.
Whatever.
There's just ones that bring them back.
Yeah. It's
So if I did anything weird, that's just because I haven't checked it over, so just let me know. Oh, also.
What are you doing? Yeah, he was like, yeah, I'm not gonna do that.
I'm just like,
I already asked about it earlier. Yeah, I should have forwarded you an email.
okay.
Yeah, I know who it is, and he emailed me, and I was just like, sorry man, sorry about this later, like, not much that can be done. They get to drop 2 problem sets, so we'll see what happens. Sounds like this will be the one they drop for 11.
Yeah, there's a lot of like, I don't know what you're doing. Oh, never mind, I found it.
Okay, so basically they were just sort of messy. That was a big part of the issue, it was just frustrating to grade.
Yeah, it feels
There you go.
more than
Amy.
what I was saying.
Yeah.